Okay, let's go and get started. This is class 2 of systems programming, and we're going to kind of go over some computer concepts again, a little more about memory, and then we're going to get into the concept of programming languages, and then the systems programming language we're going to use for this class, specifically C language. All right, so let's go and get started here. Now, the first thing is I want to review what we talked about last time. We're going to talk about another numbering system that we haven't seen before, which we're going to use in this class, which is hexadecimal numbers. And actually, before I do that, let me make an adjustment to the screen here. So I'm going to pause the recording, and then I'll come back because you can't see the slide numbers. Okay, and we're back. I just moved the thing around a little bit so you can see the slide numbers and the stuff at the bottom without it getting cut off. All right, so after that, we're going to talk a little bit about memory terminology, and then we're going to dig into programming languages and then talk specifically about the programming language C language, which is the language we're going to be using in this class. We're going to talk about why we're using that. Okay, so last time we talked about how computers work, so let's go ahead and review that. And actually, let me go ahead and go back here for a second. So I'm going to switch over to the document camera, and we're going to review that on there. So switching over to that. All right, so if you remember from last time, when we talked about how the computer worked, we basically came up with this concept that it's actually a really simple device. That basically it consists of kind of memory cells, which are really, you can just think of those as little machines or that kind of represent boxes. And those boxes can basically just store numbers in them. So you could put a 0 in a box, you could put a 1 in a box, you could put 10, you could put 50, you could put 200, whatever you want, 93, 65, 22, 14, whatever. It's just a bunch of those little numbers being held in boxes. Now, realistically, behind the scenes, these are circuits that are holding that number. And the way that it's storing those numbers is in patterns of switches that are either on or off. And the other part of this, that by itself is pretty cool. So it's a place you can store data. But what makes it really powerful is that the people who, once these were created, people thought of this thing like, well, if we can make a circuit or a machine that stores numbers, can we make a machine that manipulates those numbers and does things with them? And that's essentially what the CPU is. The CPU is just a collection of circuits that do simple operations on those numbers. And the CPU actually internally has its own little memory location, so it can store things, and those are called its registers. We have A and B is what we call them in our diagram. And then all we really needed from there was a way to connect the CPU together to the memory so it can get to the numbers that are stored in the memory. And that's what the motherboard with its system buses does. So it just provides wires that provide a way for the patterns of switches to get out of memory and into the CPU, or out of the CPU and into memory. Now, that's essentially the diagram we had last time. We can draw little kind of doors on each of these little memory cells to show that they don't all go out there at once. Basically, the CPU goes out, selects a particular memory cell, picks up the number, moves it into one of its registers, does something with that. And what can the CPU do with that? Well, the CPU just has a collection of circuitry that can do simple arithmetic or logical things with numbers, things like add, things like subtract, things like multiply, divide, compare. And then one of the important ones that we talked about, in order for these to make any sense, it has to be able to move things around. So I'm going to put that at the top. That's a really important one. It's moving the numbers from memory to the CPU, or from the CPU to memory. And then we said, well, this is great, but so we have a processor, we've got the system buses, the motherboard that connects it all together, and we've got memory. But we need a way for that to do something real, for us to access that memory and do something with it, or for us to type things in or see what it's doing. And so that's where we had that concept of adding peripherals, like a monitor. And how do we connect the monitor? Well, there's a special other kind of device that's like a graphics card or a GPU that connects to some special places in memory. So we'll write GPU. That's a little unclear. That's a G. And the document camera is a little fuzzy for some reason. But then the monitor plugs into that. Let me see if I can adjust the focus on this for just a second. That's not any better. All right, well, anyway, this is the graphics card. And part of the problem is these markers have a pretty wide tip on it to make it easier to see. GPU. All right, now, the other things that plug into that are things like the keyboard. And those plug into their own location, special location in memory. And we might plug in like the mouse or a hard drive or really any other type of physical device might plug into some of those special interface circuits. And really the only difference between those is they kind of have circuitry needed to talk to these devices in them, but it shows up to from the CPU's point of view, it just shows up as a place in memory. The CPU doesn't know any different other than, hey, stuff came into this place in memory, and that changes what's in the memory. And if I want to put something on the screen, we just write into that memory location. Notice the CPU, it doesn't have screen instructions or keyboard instructions or hard drive instructions. It just moves things around. So it doesn't even know it's putting things on the screen. It doesn't know it's getting things from the keyboard. In fact, it doesn't really know anything. So that's kind of where we had finished up last time, is the kind of conceptual model of the computer system that we have here. And one of the things, though, that remember that the memory, all it can really store numbers. And when we dug down into that, it isn't really even storing numbers. So for example, let's take one of these numbers, like let's take that 65 there. So let's say, how is that really being stored in memory? Well, if we remember, we said, well, each of these boxes is really just represented by a bank of 8 switches. And the switches could be either off or on. We use a 0 to represent off. We use a 1 to represent on. And essentially, we just use those 0s and 1s to represent a number using the binary kind of method of encoding that. And one of the things to remember about that is it works exactly like decimal. In other words, these just have place values, just like decimal numbers have place values. Like 65 has 6 in the tens place, 5 in the ones place. It has a tens place and a ones place. Or 200 has 2 in the hundreds place, 0 in the tens place, 0 in the ones place. Well, binary numbers kind of have that same concept of place values, but the place values, rather than, since it's base 2, the place values, rather than increasing by multiplying by 10 to 1 to 10 to 100, we multiply by 2. So 1 to 2 to 4, 8, 16, 32, 64, 128. All right, so that's what we did last time. So what does that 65 look like? Well, it's not going to have any 128s in it. It's going to have 164, no 32s, no 16s, no 8s, no 4s, no 2s, and 1 1. So in other words, what we represented here is this number, 65, looks like that in the pattern of switches. So if we pull this down, that means that's 64 plus, we pull this one down where there's a 1, plus a 1 equal, the decimal version of that is 65. But in the computer, in the binary version of that, it's 0, 1, 0, 0, 0, 0, 0, 1. Okay. So that's kind of where we had finished up last time. And let's go ahead and we're going to do a little bit more with that here in just a second. But let me go back to the slides temporarily. All right, so those number systems that we were using there on that previous thing we did on paper, basically decimal is base 10. That's what humans use. That's what you're familiar with because you were taught to use that when you were in preschool or kindergarten. You were taught to think in those terms, and really it's not special. The only reason we use base 10 is because historical reasons and largely because we have 10 fingers, so we think of things in groups of 10. But the computer uses binary, and why does it do that? Well, because it's switches that are inside of those memory cells in the computer that are either off or on. So it makes sense that you can only really have, if you only have two states, 0 or 1, off, on, it makes sense that you would use base 2 for that. So we're used to using base 10. We're familiar with it. Computer uses base 2 because it builds its memory out of these little tiny transistors that are essentially switches. All right, now we did conversion from previously from binary to decimal, and we're going to do a couple more of those here in just a second on paper. But the idea there is you basically write out the place values above the binary digits, and anytime there's a 1, we add that up, just like we did over on this example here. Where there's a 0, we ignore it. Where there's a 1, we add its place value. We just add all those up, and that results in whatever our result is. Okay, so what we're going to do, let's do one more example of converting from binary to decimal, and then we're going to go back and look at how do we convert from decimal to binary, which is a little bit harder, but the same concept. So let's go and do one of these first. I'll number that page 1. If you're fast forwarding or rewinding, you can easily see what page we're on the lecture notes, or the paper notes anyway. All right, so let's go ahead and move over here to a new page. And before I do anything, let me number that 2. Okay, so this is page 2. So remember, this is converting from binary to decimal. So I'm going to write that up here. Binary to decimal. Okay, so let's start off with a binary number. We'll just pick our 8 slots here. 2, 3, 4, 5, 6, 7, 8. That's my 8 bits that are making up one memory cell. And to show that's a memory cell, I'm just going to put a little box around it. All right, so I'm going to put a number in there. Let's do 1, 0, 0, 1, 1, 0, 1, 0. All right, so there's a number. That's not no significance to that. I just kind of randomly picked 1s and 0s there. Now, what number is that? So we want to figure out what that is in decimal. So if you remember, the process for that is looking back at the slides. We write out the place value for each binary digit, and any binary digit that has a value of 1, we add that up, and then the sum that we come up with is the decimal equivalent of that binary number. All right, so let's do that. So place values: 1, 2, 4, 8, 16, 32, 64, 128. Okay, so as a reminder, we're going to bring down any of these that have a 1. So this is going to be 128 plus, and then this one's going to come down, 16 plus 8 plus, and then we don't have a 4. So this one's going to come over, and that's going to be a 2. So we have 16 plus 8 plus 2 plus 128. So let's just add those up and see what we get. And that will be our decimal equivalent of those numbers. So 128 plus 16 plus 8 plus 2. So we just add all those up. Okay, so adding these up, if I were doing that, I'd say, well, that's 10. And 10 plus 8 is 18, plus another 6 is 24. So we're going to put down a 4. The 2 gets carried up there. So 2 plus 2 plus 1. 2 plus 2 is 4, plus 1 is 5. So 5 there, and nothing carries over here. So 154. So this number that we have up here is 154 in decimal. Okay, so the idea there, the places have values. If there's a 1 there, we add it. If there's a 0, we skip it. We just add them all up. Add a sum of all of the place values wherever there's a 1, and that results in the number. Okay, so we'll come back to that in just a second. But what about converting the other way? We want to go from decimal to binary. So to go from decimal to binary, that's a little bit of a different task. And that task basically involves going the other way. In other words, we're starting with a decimal number. We need to figure out, where do I put 1s and where do I put 0s in that number. So let's go back and solve that same problem. There's a little kind of process that I've written out here. But basically, write out the place value slots for the binary digits. But we don't put a 1 or a 0 in the middle. We just put little spaces there. Or in our case, we've been putting little underscores underneath them. But then what we're going to do is we're going to start at the leftmost binary place that's less than the value. So in other words, if the value is 150, we would start at the 128th place. If the value was 60, we would probably start at the 64th place. Any of them above that number get filled in with zeros. But then what we do is we say if the place value is greater than or equal to the number, so that place value we start, if it's greater than or equal to the number, then we put a 1 in that place. If that place value is less than that number, we put a 0 in that place. So now that we have a 1, we subtract that from the number that we started with, or the number that we have right now, and then we move on to the next place value to the right, the next lower one. We basically repeat that till we get all the way down to the ones place, and what we have in the slots, 1s or 0s, determines what our binary number is. So let's go back and do that example that we had done previously, but let's go the other way. So I'm going to switch to a new page here. This is going to be page 3. And this is going to be, instead of binary to decimal, this is going to be decimal to binary. Okay, so decimal to binary. Let's do that example we just did, because but we're going to do that in reverse. So we're going to start out in this case with 154, which, if you remember, that's what we had on the previous page. So we're going to start out with that 154. But this case, we want to figure out what's the bit pattern that matches up with that. So in this case, I'm going to write out my slots. 1, 2, 3, 4, 5, 6, 7, 8. So there's my 8 positions. And I'm going to go ahead and write the place values above that just so it's easy for us to remember. So up here, 1's place, 2's place, 4's place, 8's, 16, 32, 64, and 128. Now the question is, where do I want to put 1s and 0s? Now, we start at the leftmost end, in this case the 128th position, and we say, is this number bigger than or equal to that? And if the answer is yes, then that means 128 will fit into that number, so we're going to account for that. So in other words, 128 is definitely less than or equal to 154, or another way to think of it is 154 is bigger than or equal to 128. But since that's less than that, 128 will fit into 154, so we're going to put a 1 there. But since I put a 1 there, that means that the 128 that we are representing here has now been accounted for, so I need to subtract that out because I've taken 128 out of this number. So over here I'm going to say minus 128. And we're going to perform that subtraction and see what's left. So let's just do that kind of old school, first grade, second grade, whenever you learn how to do subtraction like this. So 4 minus 8, we need to borrow and make that 14, which makes this go down to a 4. So 14 minus 8 is going to be 6. So we're going to put our 6 down here. And now we have a 4 over here because we borrowed 1. So 4 minus 2 is 2. And 1 minus 1 is 0. So we just have 26 left. So now we continue along our line here. And we say, okay, this 64's place, does 64 fit into 26? And the answer to that is no. 64 is bigger than 26, so we cannot fit it in there. Does 32 fit into 26? No, it doesn't. But does 16 fit into 26? The answer is yes. So we're going to put a 1 here, but since we put a 1 there, that accounted for 16. So we need to subtract 16 out of that, which is going to leave us with 16 minus 26 is going to leave 10. Now, will an 8 fit into a 10? Yes, it will. So we've accounted for 8 of that 10. So subtract 8 from that, which is going to leave us with 2. So there 4 will not fit into 2. 2 definitely will. minus 2, and we end up with a 0, and 1 will not fit into 0, so we just put a 0 there. And there's our number, 100111010 is our binary equivalent to that number that we started with. And as a reminder, notice that matches what we had on the previous page. These match up. Now, one thing to note as a way to kind of double check yourself is that if you get to the bottom and you have something other than 0 here, then you've done something horribly wrong. So if you wind up with something that is not 0 when you get to the bottom, you wind up with a negative number, 5 left over, then you've messed up somewhere up in here. But really, you just start at the top, just apply that process, and when you get down to 0, you get all the way through all the bits. The binary number that's in there is going to be the representation of that decimal number. All right, let's try one more example of this, just for completeness here. So get a clean paper, and this is going to be page 4. So here we're going to do one we haven't done before. We kind of cheated on that other one and picked 154, which we'd seen before. So let's pick a number like let's do 99. And this is more decimal to binary. So 99 equal, let's put our slots, 1, 2, 3, 4, 5, 6, 7, 8. We need to figure out where I put 1s and where I put 0s. So let's put the place values up there just as a way to remind ourselves. 1, 2, 4, 8, 16, 32, 64, 128. All right, so starting at the top, 128. 128 will not fit into 99. So that's going to be a 0. 64 will fit into 99, so that's going to be a 1. Subtract 64 out of that. So 9 minus 4 is 5. 9 minus 3, or 6 is 3. So we have 35 left. Will 32 fit into 35? Yes, it will. So minus 32 leaves 3. So a 16 won't fit, an 8 won't fit, a 4 won't fit, but a 2 will. So minus 2 leaves 1, and then there's a 1 there, so minus 1, 0, 1. So there's my bit pattern, 0, 1, 1, 0, 0, 0, 1, 1. And that becomes our answer. So in this case, 99 decimal equal 0, 1, 1, 0, 0, 0, 1, 1 in binary. Okay, so hopefully you have a handle on how to do those conversions. You can go from binary to decimal, decimal to binary. And it's really kind of a similar process. One of them, though, we just add them all up wherever there's a 1. The other one, we have to figure out where the 1s go by starting with a number and then working our way down from the larger place value to the smallest one. Put a 0 wherever it won't fit, put a 1 where it will, subtract out the number whenever we put the 1. Okay, so you should be able to do that. And so we looked at an example. And now a couple quick things about decimal versus binary. Decimal is clearly natural for humans. It's what you're used to dealing with because you've been taught that your whole life. But binary is what's used in computers because it's what's natural for computers since it stores things with switches that are either off or on. But they really aren't that much different. They all have place values. You sum up the place values. The place value acts as a multiplier. You sum all of those up. And it also works for fractional numbers where you have things on the other side of a decimal point where you have the tenths place, hundredths place, thousandths place in decimal. You could do the same thing but have the 1/2 place, the 1/4 place, the 1/8 place, and so forth. So really, they're not all that much different. It's just one we're used to dealing with and comfortable with because we see it a lot and use it a lot. The other one is what computers use because of the way they represent the data. Now, a couple notes about that, though, is that decimal is definitely more compact and easier for us to use because we're more familiar with it. But also notice Here, just quickly, let me switch back over to here. Notice that it's more compact, meaning this took 2 digits of decimal where it took 8, or if we leave off the leading 0, 7 to represent it with binary. So decimal is definitely more compact. Like on that previous example with the 154, that took 3 digits of decimal for 8 of binary. And so it's a lot easier for us to remember a number like 154 than it is to remember 100111010. And as an example of that, you might remember on that next example that we did where we did 99. That's easy to remember, but if I asked you what's the binary pattern for that, you probably have a hard time remembering exactly where the ones were, where the zeros were to come up with that. So it's easier to remember these, partially because we're used to dealing with it, partially because it's more compact. There's less things to remember there and less chance for us to leave out a 0 or 1 or transpose them and get them backwards or something like that. Okay, so one thing to notice is that decimal rolls over to needing new digits in different places than binary. So decimal is more compact, it's easier for us. Binary is really how things are stored in the computer. And the decimal rolls over to needing new digits at a different place than binary does. And that can make it hard to visualize a decimal number without its binary representation, without doing the full conversion process. So what we'd like to have is some sort of more compact system, kind of like decimal, but one that matches very nicely or very naturally onto the way the computer actually stores numbers in binary. And so that's what we're going to take a quick look at today, is this other number system called hexadecimal. And hexadecimal, where decimal is base 10, where binary is base 2, hexadecimal is base 16. And there's a good reason for that we'll look at here in a second. But that means the digits base 16 are basically 0 through 9, just like we have with decimal, but then they needed 6 more digits. They could have come up with other symbols here like happy face, heart, club, spade, unhappy face, bunny rabbit, or whatever. But they decided to just use A, B, C, D, E, F because those already have an order associated with them. They were already characters we're used to dealing with. So we just go 0 through 9, A through F, and that represents the hexadecimal digits. Now, each one of those digits maps very nicely onto 4 bits of binary data. So that makes it compact like decimal, in fact, a little more compact than decimal. And it also makes it so it maps very naturally onto binary numbers. It's more human-friendly than binary and more computer-friendly than decimal. So it's kind of the best of both worlds. So let's take a look at how it works. All right, so first off with binary, here's 4 bits. And with 4 bits, there are 16 total combinations that we can have of those, ranging from 0, 0, 0, 0, all the way down to 1, 1, 1, 1. Now, if we go through the counting sequence with all of those, so 0, 0, 0, 0, 0, 0, 0, 1, the next one 0, 0, 1, 0, 0, 0, 1, 1. And if this counting sequence seems confusing, it's really the same as like decimal, except that we only have 2 digits. In other words, when you get from 0 to 9, you need to go to a new digit. When you get to 10, you reset the one that you're on back to 0 and then use a new digit. But in binary, we only have 0 and 1. There's no 2, there's no 3. So when I get to 1, this is all filled, so I reset it to 0 and I roll over to the next one. And then when these are both filled, we reset those and roll over to the next one and so forth. Anyway, with those 16 possibilities that we can get, we wind up with associating one of the hex digits with each of those. So in other words, 0, 0, 0, those 4 bits are represented by a 0 hex digit, where 1, 1, 1, 1 is represented by an F hex digit, and all the ones in between. Now, before we move on from that, if you want to recreate this table or need to, or think through that counting sequence, there's a really easy way to make sure you did it right. And that is, if you look at the least significant bit, the least significant digit here, you'll notice that we start with all zeros, but then you notice the least significant digit only, it goes 0, 1, and then it alternates, 0, 1, 0, 1. So the ones place alternates every other one. And if we go to the twos place here, it alternates every 2. So 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. If we go to the fours place, it alternates in groups of 4. we go to the eighths place, it alternates in groups of 8. So it's really easy to recreate that table or look at that and make sure it's correct by just kind of looking at each of the vertical stripes of the bits. And does the ones place alternate every other one? Does the twos place alternate every 2? Fours place every 4, eighths place every 8, and so forth. Okay, now, so each hex digit, these here, represents a 4-bit pattern. And one of the ways, things that you'll see a lot is in programming and in computer science, we need a way to avoid confusion between like the number, a number that's written in hexadecimal or a number that's written in decimal or some other base. And so we tend to use this prefix 0x. So that's not really part of the number. That's just a thing saying, hey, the thing that's following this 0x, that's going to be hex digits. So in other words, when I see this 41, I know that's not 41. That's 41 hex. And the reason for the 0x is just to avoid confusion. You might also see sometimes where they'll put something like the hex digits with a lowercase h following it, like 41h. That also is a way of representing or indicating a hex digit. Okay, so here are some examples. Down here, 0, 0, 0, 0, 0, 0, 0, 0. We divide that up into groups of 4 bits, and that creates 0x00, which is decimal 0. Or this one, we divide it up into the first 4, 0, 1, 0, 0. If we look that up in our table, 0, 1, 0, 0, that's a 4. And the next one, 0, 0, 0, 1, that's a 1. So that's 41 hex, 0x41, which is a 65 decimal. And I've got some other examples here as well, including like 1, 1, 1, 0, 1, 0, 0, 0 is E8, which is 232 in decimal. And all ones is FF, which is 255 in decimal. Now, the cool thing about that, though, is notice that this went from needing 1 digit to 2 digits to 3 digits, where in hex, with this 8-bit binary number, it's always 2 digits here, 0, 0 through FF. And when we get to FF, we have filled that up completely because we filled this up completely. And that's the beauty of hexadecimals. It's much easier for us to remember. It's much easier for us to think about. And it's very easy for me to look at, if you know how it works, to look at something like 4-1, and I can immediately visualize what that looks like in memory. Where 65 is a little harder. I have to do that mathematical process. Or 146 is, I got to figure out, okay, well, there's a 128, and then what's left? You have to do subtraction. But if I look at 9-2, I can immediately see 9 as 1001 and 2 as 0010. As long as you know this pattern or could write this pattern out, you can really easily convert from hex to binary. And notice it's also really easy to convert from binary to hex. And so those conversions wind up being really easy to perform. Hexadecimal to binary, we look up in the table the 4-bit pattern, and then that goes with each hex digit, and then we write it down for each of the hex digits. Binary to hexadecimal, same thing, we just use the table in the opposite direction. Divide the binary number into 4-bit blocks, look up the 4-bit block in the table, and then write down the hex digit that went with it. Very easy to convert. In fact, once you get used to that, you can do that in your head very easily. So if I were to say like 8-3, you could immediately know what 8-3 was. 1, 0, 0, 0 is 8, and then 3, 0, 0, 1, 1. So 8-3. So I can do that in my head, and I can do that either way. If I have a binary number like 1, 1, 0, 0, 0, 0, 0, 1, I can immediately see that that's C1 in that conversion. So really, best of both worlds, compact notation, but matches up perfectly with binary numbers. And there are those examples again there that we saw earlier. And as practice, you might want to pause this and take a look at each of these and look at, okay, 1, 2, 3, 4. There's 4 bits there. That's a 9, 0, 0, 1, 0. That's a 2, 9, 2. Okay, now before we move on away from this, I do want to at least go through a little bit of memory terminology here, which I'm sure you've heard these before and maybe even used them, maybe not, maybe some of them you have, some you haven't. But bit is where we started with, or where we got to last class with, that's a single switch in memory. So each one switch in memory is 1 bit. There's nothing smaller than that. The switch is either off or it's on. Can't be part way off, can't be part way on. It's either 0 or it's a 1. That's 1 bit. Now a nibble is 4 of those bits together. So in other words, if I take 4 bits, that's what we would call a nibble. And that's represented by a single hex digit. So kind of looking back over here, each of these is a nibble. So there's 16 possible distinct nibble patterns for 4 bits, each one represented by a hex digit. Now a byte is 8 bits, or 2 nibbles. Also, that's sometimes called an octet. A word is 2 bytes. That's 16 bits. A D word or a double word is 4 bytes, which is 32 bits. A Q word or a quad word is 8 bytes at 64 bits. A paragraph is 16 bytes, which is 128 bits. And so you'll tend to see these kinds of things, this terminology used quite a bit. So if you see word, just know that's 2 bytes. If you see double word or D word, that's 4 bytes. Quad word, that's 8 bytes or 64 bits. Now, there's some other ones here that get into larger sizes, like a kilobyte, which is shortened as K or KB or KIB sometimes. But that's 1,024 bytes. And notice it's not exactly 1,000. It's 1,024. And the reason for that is 1,024 is a power of 2. Again, it matches up nicely on the way the bits are organized in the computer. And a megabyte, or a meg, or sometimes shortened as M or MB or MIB, that's 1,024 kilobytes. So notice it's not a million bytes, it's actually 1,024 kilobytes, which are 1,024 bytes. And then gigabyte is 1,024 megabytes. Terabyte is 1,024 gigabytes. And then it goes up from there into petabytes and exabytes and zettabytes and yottabytes. And this yottabyte is really not particularly useful right now. For example, the whole size of the internet is estimated at a couple zettabytes. So we're 1,001, probably about 1/500th of a yottabyte right now with everything that's stored on the entire internet. But you will have encountered terabytes, gigabytes, megabytes, kilobytes, and then all of these other things probably in your daily life. Okay. Now, one of the things is individual memory locations are identified by a unique number that we call an address. And the addresses are a lot like mailbox numbers. Like if you go to the post office and you look and they have that giant like wall of like little post office boxes, they all have like a number on them. And when somebody that has one of those boxes gives out their address, their mailing address, they say P.O. box number, and they use that number to refer to it. Well, the same thing is true in the computer system. That the computer system just has all of those memory boxes that we saw in this diagram here. Each one of these has an address associated with it. Backwards. Has an address associated with it. And there are a lot of possible addresses because there are a lot of memory locations in most computer systems. So if you have a cell phone with 128 gig of memory, or you have a PC with a large amount of memory in it, those all have a unique number that identifies them, and that's how the CPU knows which ones it's accessing to either get data or store data back into that number. Okay, so there might be a quiz on what we've covered so far. Next class, that's a hint when I tend to say, hey, that would be a good thing to have a quiz on. That would be a good sign that you should maybe study that stuff. So if you want a little more detail on that, I would study binary numbers. I'd study converting binary numbers to decimal numbers, converting decimal numbers to binary numbers, converting hex numbers to both decimal and binary, and I would probably study converting binary numbers to hex numbers, hexadecimal numbers, and so forth. And you might even want to kind of remember these things. I don't expect you to sit down and memorize these. A lot of them make sense. Bit, nibble, byte, word, D word, Q word. Actually, for some older computer systems, they had a thing they called a crumb too, which was 2 bits, you don't see that used very often. But it's interesting. It went from being like cute and clever, bit, nibble, bite, crumb, or bit, crumb, nibble, bite, to now being all serious with words and D words and things like that. But if I were you, I would go ahead and maybe study that. So I'm going to go ahead and we'll take a quick break here. So I'm going to pause this video, and the next video we're going to continue on with concepts of programming. So let me go ahead and just stop this here, and then we'll continue on in the next recording with what we're going to cover today. But remember, there might be a quiz. All right, see you soon.